for example, if we look into the first rule of this grammar B or B. So, for the sake of our understanding, so we are writing it as B. So, B producing B 1 or B 2. So, like this. Now, so we will assume that the true and false transfer points for the entire expression B is known. So, it is part of, so B is part of some bigger expression, like say, so let us do it like this. If some Boolean expression, then I have got a block of statements S 1 else S 2, where S 1 is a block of statements and S 2 is another block of statements. Now, if you look into the parts tree for this, so it will be something like this: S producing if, then a portion of the parts tree which will correspond to B, then there will be a portion of the parts tree which corresponds to S 1, and there will be a portion of the parts tree where I will have this S 2. Fine. Now, it is assumed that when I am doing this reduction, so if B is true, it will. So, since all these reductions have already been done, so this S 1 and S 2's position in the 3 address code file, so they are known, isn't it? Because by that time the codes have already been generated. So, I can very easily tell what is the offset of the code S 1, what is the offset of the code S 2 in the full 3 address code file, the file that contains the 3 address code, what are the offsets of these positions. So, naturally, I can assume that for this B dot true and B dot false. So, these two pointers where they should point to. So, that is known when I am going to do this reduction. Similarly, if I so just to extrapolate that fact. So, if I have got a rule like this, so B 1 or B 2. So, we know that when I am doing this, so for this this B, so we already know the true and false pointers for that. So, where the true and false should go, but then for the now if now what the situation is that if B 1 happens to be true, then since this is an OR operation. So, if this is the true branch and this is the false branch, then B 1 being true, it should follow the true branch of B, and B 1 so B 2 be so similarly B 2 being true, so it should follow the true branch of B. And similarly, if B 1 is false and B 2 is false, if both are false, then only it should go to the false branch. Now, it is a bit confusing, because I said that when I am doing this reduction. So, in this particular case, when I was doing this reduction, these targets were known, where S 1 and S 2 are in this file that were known. But here my B expression is not yet over. So, I do not know where the so I am in the I am actually parsing somewhere here doing the parsing at this point. So, at that time I have not reduced the S 1, I have not reduced S 2. So, as we were looking into the numbering policy of this reduction, so you see that these numbers that are appearing for this tree, so they are much less compared to these numbers and these numbers. So, they have not yet been reduced. So, they are that they will come later. So, naturally, for a single pass type of operation, so it is difficult, but if we assume that my compile the code generation phase will be in a 2 pass fashion. So, in the first pass, so you can identify all these jump targets, okay, for B dot true and B dot false. So, that in the second pass, while generating the actual code, so you can just use those or you can just use those addresses. Of course, you can do something else also, that we will see for single pass compilation. So, we need to do some sort of backpatching type of operation. So, that we will see later. So, for the time being, it is assumed that we have got this whenever we are having this particular rule B producing B 1 or B 2. So, it is assumed that the true and false transfer points for the entire expression B are known. Now, if B 1 is true, B is also true. So, we need not evaluate B 2. So, B 1 appears to be happens to be true, then B 2 need not be evaluated. Without evaluating B 2 also, we can say that the whole expression B is going to be true. So, this is called a short circuit evaluation, because we will not evaluate B 2 if B 1 is already true. Similarly, if B 1 is false, then of course, we cannot tell anything, because now I need to evaluate B 2 also, and if B 2 is also false, then it will be then we have to follow the false label. So, the way the code is that the semantic actions or the syntax directed actions are written is like this, that B 1 dot true is made equal to B dot true. So, since you assume that we already know B dot true, so B 1 dot true will be like that, but for B 1 dot false I do not know where to go. Okay. So, that way I generate a new label. So, this new label is say L 1. So, B 1 dot false equal to L 1. Now, B 2 dot true equal to B dot true, B 2 dot false equal to B dot false, because I will first have the code for B 1, then I will have got the code for B 2. So, if B 1 is not true, then it has gone like this. So, it has gone like this, and then I will be so this B 2. So, at the end B 2 dot false will be equal to B dot false, and this B dot code is, it will have the code for B 1, it will have the code for B 2, and then but in between there will be a label that will get inserted. So, here you see that B 1 dot false. So, we have got the label. So, that will be inserted here. So, B 1 dot false colon. So, that will be inserted, then I will have got the code for B 2 dot, I will have the portion for B 2 dot code. So, what the situation, the final situation for B dot code will be something like this. So, here I will have got the code for I will have the portion for B 1 dot code. This is the B 1 dot code, and after that I will have this new label that is there. So, this new label L 1 has been generated. So, this is so B 1 dot false contains the label. So, this is L 1, suppose the new label that is generated is L 1, and after that it will be the B 2 dot code will come. So, after B 1 dot code, this L 1 will be generated, this L 1 label will be generated, then this B 2 dot code will be generated. So, it will be going like this. So, this after this B 1 dot code is over, see this label will get inserted, and then this B 2 dot code will be put at the end. So, this way I can generate the code for this B 1 or B 2. So, we will look into the other rules, other grammar rules for generating the code for other Boolean expression, other rules like B equal to B 1 and B 2. So, in that case, if B 1 is true, then I have to evaluate B 2 also, but if B 1 is false, then it is a short circuit. So, if B 1 is false, so B 1 dot false is made equal to B dot false, then B 2 dot true is so B 1 dot true is new label, then this B 1 dot false is B dot false. So, that means it is a short circuit, and then B 2 dot true is B dot true, B 2 dot false is B dot false, then B dot code is the concatenation of B 1 dot code, then this particular label B 1 dot true colon, and then B 2 dot code. So, this that way I can have this B 1 and B 2. Then not of B 1. So, B 1 dot true is B dot false, B 1 dot false is B dot true, and B dot code is equal to B 1 dot code. So, no new code has to be generated, but this true and false pointers, so they are to be reversed. So, wherever the B 1 so B is B dot false, wherever it was going. So, they should be we should go there if B 1 is becoming true now, and wherever it was going on B becoming true. So, on B 1 becoming false, we should go there. Okay. So, then B within bracket B 1. So, this is also very simple. So, B 1 dot true equal to B dot true, B 1 dot false equal to B dot false, B dot code equal to B 1 dot code. So, like that. Now, B producing true. So, this is B dot code, it will generate a go to B dot true. So, then because we know it is definitely true. So, that way I do not have to evaluate anything. So, this is B dot code will be. So, this particular line will be generated go to b dot true. So, b dot true is already known, the target is known, so it will go there. Similarly, b dot false is like this. Now, id1 reloop id2. So, this will generate the two statements. So, if id1 dot place relational operator id2 dot place go to b dot true, otherwise it will go to b dot false. So, that way this id1 reloop id2 will be done. So, how does it help us in generating the generating code? So, this helps because I can have the short circuit of Boolean operators and all. So, I do not evaluate the complete expression, and so that helps. Okay. In many programming languages you see this is helpful, like see suppose I have got this check. So, I have got an array in my program integer a100, and at some point of time I need to check whether if ai is greater than 50, then something. Now, one problem with this type of situation is that, so if this index I itself has become more than 100, the value of the expression I itself is more than 100, then whenever I am trying to do this ai access, so this can generate some violation of condition. Okay. So, there is some runtime error may occur. So, it is a safe practice that we write like this: if I less than 100, less or equal 100 and ai greater than 50, then I have got the piece of code. Now, here you see that if I happens to be more than 100, then this part itself will evaluate to false. So, I will not go into this evaluation, and it will, so it will not try to access some arbitrary memory location to get the value of ai. So, that way my code execution is much safer. Okay. So, this is too good, like for this short circuit of this Boolean expression evaluation. So, this is really helpful. However, the way that we are generating the code, it has got problems, because the first thing is that it makes the scheme inherently two pass procedure, because in the first pass all the jump targets will be computed, and in the second pass the actual code generation will be done. So, that is required, because I need to have this b dot true, b dot false. So, those pointers, their destinations are calculated before we generate the code. However, so that makes it a bit cumbersome also. So, there is a modification to the grammar, so that we can make it a single pass approach. So, single pass approach, it can be developed by modifying the grammar a bit and introducing a few more attributes. Okay. So, a few new procedures, and the generated code can be visualized as an array of quadruples. So, that way we can so that is correcting some portions, some corrections can be carried out in the code that is generated. Basically, when the jump targets become known, then only we can tell the address. Like for example, if I have got a statement like if some Boolean expression b, then S1 else S2. Now, while parsing this b, so I have got at several points the b becomes true or b becomes false, like that. So, at those points I need to transfer the control to either S1 or S2, but until and unless the code for b is over. So, if this is the file where I am writing the code for this 3 address code. So, until and unless the code for b is over, I cannot start the code for S1, and until and unless the code for S1 is over, I cannot start the code for S2. So, when I am at these intermediary points, I really do not know this particular offsets, the offset of S1 and offset of S2, because it is all dependent on size of B1, size of S1, etc. So, I need to do something, so that in the first pass I can take it as I can know that the offset values. Okay. The second pass I do that. However, in the single pass procedure, so we have to modify something so that we can generate the code. So, how is it being done? So, the attributes that we are talking about, new attributes apart from that b dot true and b dot false. So, we have got a true list and a false list for every Boolean expression. So, b dot true list, it is the list of locations within the generated code for b at which b is definitely true. So, as I was telling that if this is the portion of this is the parse tree for b part. So, this is the parse tree for b. Suppose at these points in the parse tree the b expression is definitely true. So, we put all these locations in a list called b dot true list. Similarly, there may be a few locations where b is definitely false. So, they are put onto the list b dot false list. So, in b dot true list, it is the list of locations within the generated code for b at which b is definitely true, and once defined all these points should transfer control to b dot true. So, when I am generating the parse tree for b, so at that time I do not know what is b dot true and b dot false targets, but after some time they will become defined. So, for example, that if then else statement, that then part and else part, the statements they will come after some time of parsing. So, at that point, so this jump targets will be known, and for the non-terminal b. So, we have note down the true list where all these points of all these points at which the b is true. So, that that values have been kept. So, at all those places we can replace the address the jump address that was left as blank at that point. So, they can be filled up with this jump this new address, which is this b dot true or the address of S1 in if then else statement. Similarly, b dot false list. So, it contains the list of locations within the generated code for b at which b is definitely false, and once defined all these points should transfer control to b dot false. So, they should so I should have the all controls transfer to b dot false. So, all these points I can do some correction in the target code that is generated, so that they are rectified, and now they contain the address of b dot false as their jump target. Some more functions are also necessary, like make list I. So, it creates a new list with a single entry I. So, and so this is an index into the array of quadruples. So, some slide earlier we have said that generated code is visualized as an array of quadruples. Okay. So, here also we say that this make list I. So, this is an index into that array of quadruples. Then merge list of list 1 and list 2, it returns a new list containing list 1 followed by list 2. So, the merging of two lists. Then backpatch list target. So, this will insert the target as the target label into each quadruple pointed to by entries in the list. So, this will be, so this list is containing all the places where these jump targets are not yet filled up. Okay. Now, for them, so if we come across the correct target with which to which these all these control should jump to, so that is called target. So, all those locations they will be filled up with the value of target, and there is a function called next quad that will return the index of next quadruple to be generated. So, many a time we will need to know what is the address of the next piece of code that will be generated. So, the next quadruple of code that will be generated. So, that is by this next quad function. So, the grammar that we will have now is a modified version, B producing B or MB, B producing B and MB, not of B, within bracket B, ID develop ID, true, false and epsilon, M producing epsilon. So, this is a, so in this particular case you see what has been done, we have introduced a new dummy variable M. Okay. So, we have introduced a new dummy variable M. So, which we call and this is dummy because ultimately I am replacing it by M producing epsilon. So, it does not have any effect on the M. Okay. So, it does not have any effect on the grammar, but this will be useful for knowing some addresses and modifying the proper values, inserting proper jump targets and all. So, this M, it has got an attribute called M dot quad that can hold index of the of a quadruple. So, you can say m dot quad equal to some quadruple value. So, that will tell us that will hold the that can be assigned some index of a quadruple. Now, how is it going to be used? So, it may be clear by looking into say this particular rule B producing B 1 or M B 2. Okay. So, before this execution of B 2 starts, reduction M producing epsilon has already taken place. So, if you look into the parts tree, so this will be like this. So, B producing this B 1, then M B 1 or then M and this B 2, and this M produces epsilon. So, this is the parts tree part. Now, as we have seen previously by that number, the policy of that numbering of those reductions. So, first these reductions will be numbered, then this reduction will be numbered, and then only these reductions will be numbered. So, before these B 2 reductions are made, B 2 reductions are numbered or B 2 reductions take place, just before that this M producing epsilon. So, this reduction will take place. So, since this M producing epsilon is not going to give me any new code. So, this M dot quad, which is the address of the so I can make that it can hold the index of a quadruple. So, if there is a function called next quad, so that gives me the index of the next quadruple to be generated. So far we have generated till say up to this point we have generated say 105 quadruples. So, this next quadruple is 106. So, what we can do is that we can make this M dot quad equal to 106. So, that will mean that that will be exploited later for correcting some addresses in the table. So, how is it being done? So, let us see in the successive slides. So, this is the full set of rule that we have. So, we have got this first rule is B producing B 1 or M B 2. So, then what we do? So, at this point, so B 1 and B 2 they are true list and false lists, they are known, and this M it has got the quad. So, as I was telling that at this point, so I have got see this B 1 or M B 2. So, this was the situation, and B 1 true list has got all these points, B 1 false list has got this point, B 2 true list has got this point, and B 2 false list has got this crossed point say. So, this true list and false list have been done. Now, with so what will happen if B 1 is false? So, if B 1 is false, so I have to come to the B 2 part. So, and B 2's evaluation starts at a portion when B 1's evaluation ends, and B 2 evaluation starts at this point, and that is that will be. So, before that this M producing epsilon. So, this will be done, and for this M producing epsilon the corresponding action that we take is M dot quad equal to next quad. So, this M has got a special attribute quad, okay. So, which holds the index of the next quadruple to be generated in the code generation process. So, this M dot quad is next quad. So, in this particular case, so it will hold the start address of computation of B 2. So, this way so this backpatch B 1 false list with M dot quad. So, all these false list, all these positions their targets were not known. Now, so once this M dot quad is known, so all those values should be backpatched with M dot quad. So, all those blank locations they can be filled up with the value of M dot quad. Then B dot true list. So, it is a so for B dot for B's true list is the collection of all true points of B 1 and all true points of B 2. So, this is the true list of B 1 of B. So, merge list B 1 true list and B 2 true list. So, merge list means it will merge the two lists and get the overall thing, and B false list is B 2 dot false list, because B 1's false list have already been backpatched with start address of B 2. So, it will branching from here to here in the execution, and then B2's false list. So, that will be so B's false list will be same as B2's false list. Similar type of rule can be made for this AND. So, B1 and M B2. So, we backpatch B1 true list with M dot quad, B true list is made equal to B2 dot false list, and B false list is made merge list of B1 false list and B2 false list. So, this is just the complementary version of this OR rule, the AND rule. Now, not of B1, B producing not of B1. So, B dot true list equal to B1 dot false list and B dot false list equal to B1 dot true list. Similarly, B producing within bracket B1. So, this is true list and false list remain unchanged. B producing true. So, this will be this will have this this will generate a code, and this at that point the expression is definitely true, because the expression itself is being reduced by the rule B producing true, true being the constant token for this is the constant value for the Boolean expression true. So, that is this emit go to. So, this has to be filled up. Okay. So, where to go we do not know, because once this target will be known, then only this can be filled up. So, this way it is left like this, but before that this next quad function has been called. So, this is a point where the expression is definitely true. So, that so wherever this go to is generated. So, this particular quad. So, if it is quad number say 100. So, this is a place where I have to do the correction. Okay. So, this make list next quad. So, it will make a list with 100 as one of the entry. Now, there may be several other points that will come where B is definitely true. So, all these will be put into this chain. Okay. And they will be, that will be called B dot true list, and then they will be backpatched with the when this go to target will be known. So, all these places will be filled up. So, say the target becomes a 200. So, I will be writing 200 here in that case. So, the code will be corrected. Then ID1 relope ID2. So, here also I have got the situation like B dot true list equal to next quad, B dot false list equal to next quad. Then emit if ID1 dot place relational operation ID2 dot place go to, and then again this part is not known. So, this will be filled up later when this B dot true list this B dot true will become true be available. So, they will be backpatched with that. Okay. So, this way we can have this Boolean grammar rules. For them we can have the corresponding actions. Now, so we will look into this example. So, this x greater than y or z greater than k and not of r less than s, and this is the corresponding grammar that we have, corresponding parse tree that we have. So, we initially have this b, and since OR is of least precedence. So, it is divided by this rule b producing b or m b to m b. Then after that, so this OR is ID relope ID. So, this this first b is ID relope ID. So, this is x greater than y. Then the second one is now this m is epsilon. Now, so this now this since OR is of the least precedence. So, this is the second part of this OR. This whole thing is the second part of this OR, and it has again had got two things like AND, NOT, and etc. So, first this before the AND. So, this z greater than k. So, that part is generated. So, b and m b, that is generated, and this from this b we get ID relope ID, and that is z and k, m giving epsilon, and then this b is gives me not of b. So, not of b and b giving me ID relope ID. So, r less than s. So, this way we can generate we can write down the parse tree for this particular example string using the Boolean grammar. So, we will look into the code generation for this in the next class.